All right, last section for this chapter is about gas mixtures and molecular speeds. So an example of a gas mixture would be like our atmosphere. It's a bunch of gases that are mixed together. They are not chemically combined, aka they are not bonded. So in our atmosphere we have nitrogen and oxygen, just to name a couple, but just because oxygen and nitrogen are found in the atmosphere together does not mean that they are necessarily bonded together. And then we're going to look at how gas molecules move in relation to their size, because as we all know, size matters. What causes gas pressure? Reviewing here. How much gas can influence pressure, but what actually causes the pressure? Not the temperature, but again, that influences the pressure. What actually causes there to be gas pressure in a container? Think back, this is like all the way back to like 14.1. What causes the gas pressure is the actual collisions between gas particles and what else? And the walls of the container. So, like Cora had said, the temperature influences this pressure. So when we increase the temperature, what happens to the rate of these collisions? There's more collisions, and so how does that influence pressure? It increases the pressure. So if we decrease temperature, what happens to the collisions? We decrease that, and then therefore we are also decreasing pressure. So what happens to gas pressure when we add more gases to the container? We don't change the container shape or size. We just change the amount of gas. Yes, so if we increase the amount of gas, we also increase the gas pressure. Does it matter what the gas is? So if we're putting more gas in, does it matter if it's oxygen or nitrogen or chlorine gas? Doesn't matter. No, the type of gas does not matter in terms of gas pressure. So we have these things when we have a mixture of gases called the partial pressure. This is the contribution that one gas makes to the total pressure when the gas is part of a mixture. So if we have 3 different gases in a mixture of gases, each of those 3 gases has its individual pressure that contributes to the total overall pressure felt from that container. Does that make sense? Okay. So Dalton's law of partial pressure says the total pressure of a mixture of gases is equal to the sum of all of the partial pressures of the component gases. So here's your little formula for that. The pressure from the first gas plus the pressure of the second gas plus the third gas, fourth, fifth. If there's 17 gases, you're going to have up to P17. Does that make sense? Okay. Here is a visual representation. Your pressure from the first gas, not so high. Your pressure from your second gas, a little bit higher. You add them together, so your overall pressure will be higher. Your P total should be the highest value. Let's spell it correctly. Highest value for P out of all of them. That's shown here if you look at these little pressure meters here. This one is the lowest at here. It increases. P2 is a little higher. And when you add them together, your P total is the highest pressure of them all. So in order to do these problems, when we look at partial pressures, you need to first be able to calculate mole fractions. This is the ratio of moles of one substance in a mixture to the total number of moles of all the substance, or like the total substances. So a flask contains a mixture of 1.2 moles of hydrogen gas and 2.91 moles of oxygen gas. If the total pressure, or P total, is 104 kilopascals, what is the partial pressure of each gas? So we are looking for the pressure of the hydrogen gas and the pressure of the oxygen gas. So in order to do that, we need to look at the mole fraction. So when we look at the mole fraction for hydrogen, you take the total amount of hydrogen gas present, so 1.24 moles, that comes from the problem, right here, over the total in the system. So that would be the 1.24 plus oxygen, which is at 2.91 moles. So when you do that, you get the mole ratio here of 0.2999 for hydrogen. And since it's asking for the partial pressures of both hydrogen and oxygen, you need to repeat this step, but instead of doing it for hydrogen, you need to calculate the mole fraction for oxygen gas. So in this particular one, what would be our numerator for oxygen gas? Very good, 2.91 over the total, 5.1. Is that what 1.24 plus 2.91 is? Okay. And then here we get 0.701. So then to figure out your partial pressures, the partial pressure of hydrogen, you use this value from your mole fraction for hydrogen, 0.2999, times your total pressure of the system, which is 104. And the partial pressure then of hydrogen gas is 31.3 kilopascals. Repeat that process, except instead of the value for the hydrogen, you use the mole fraction for oxygen, which was the 0.701, times your total pressure, and we get 72.9 kilopascals. All right, so one technique in the lab to collect gas for these experiments and to measure quantities is to use water displacement. So in order to do that, you need two containers. The first container you fill completely to the brim with water, and you place it in a dish, a second dish, that has enough water into it so that the water from container one doesn't move. Okay, so it has nowhere to drain to. Then you put a little siphoning hose in it, and it allows whatever reaction to take place and the gas to escape, and then you can collect the gas off in another container to measure the quantities and the characteristics of that gas. So in order to do any sorts of calculations in which gas is collected via water displacement, in your textbook and in your problems, it'll say a gas was collected over water. That's when you know water displacement was used, and that also indicates to you that you need to know the vapor pressure of the water at that specific temperature must be known. You don't have to do any calculations to figure out the vapor pressure of water at that temperature. Just look at this handy dandy chart. Okay? I will provide you this chart come tests or quizzes. When you collect gas by water displacement, if the water level inside of the first container is the same as the outside of the bottle, as if their pressures are the same, if the levels don't change, that means the water pressure and the vapor pressure are the same. So right in this first example, the water pressure and the atmospheric pressure are the same. There's no changes. Here, in the second example, there was a change in atmospheric pressure, or rather, there is a difference in the atmospheric pressure than the water pressure. And that causes the difference in the height of the water to go from this column to this column, A to B. So to do these problems, we can practice that. A certain experiment generates 2.58 liters of hydrogen gas, which is collected over water. Like I said, collected over water indicates you need to know the vapor pressure of the water at 20 degrees Celsius, and the atmospheric pressure is 98.6 kPa. Find the volume of dry hydrogen that would occupy STP. So dry hydrogen simply means not collected over water. So if it was just found in the atmosphere. So bits of information you know a volume. It's given at 2.58 liters. That's hydrogen gas. Your temperature is 20 degrees, but per most of our calculations in this chapter, we do have to convert that to Kelvin. 293. You know your P total is 98.6 kilopascals. And we need to figure out the partial pressure of hydrogen. And once we do that, then we can use the combined gas law to figure out the volume of hydrogen. We don't care about any of the other gases that are present contributing to this pressure. It is just asking about the volume of hydrogen. So to figure out your partial pressure of hydrogen, you have to subtract out the pressure of the water vapor. So you look back on the table from this previous slide, and you look at 20 degrees Celsius, and it wants your vapor pressure. So our vapor pressure of water is 17.54 millimeters of mercury. So pressure of the water is 17.54 millimeters of mercury. So before we can do a subtraction, what do we have to do with our pressures? We have to convert them to the same units. It doesn't matter if you go into millimeters of mercury or kilopascals. I happen to go into millimeters of mercury. I converted the 98.6 into millimeters of mercury. And for time's sake today, I think we just need to get that number, 739.7 millimeters of mercury. So to figure out your partial pressure of hydrogen, you take your total pressure minus the pressure produced by the water vapor, and that will give you your partial pressure of hydrogen. So once they're converted to the same units, 739.7, which is your total pressure, minus the 17.54 contributed by the water vapor. And so the pressure of hydrogen is 722.2 millimeters of mercury. So that was the first step. Then your second step is asking you to find the volume of dry hydrogen that would occupy at STP. So here we are comparing a volume and a temperature and pressure that's not at STP, the parts that were given to you previously in the problem, and they want to know what that would be at STP. So that gives us, or we should use the combined gas law, which, if you remember, is P1 V1 over T1 equals P2 V2 over T2. So all of these initial pieces of information would be your first set. So this volume of 2.58 liters is your initial volume, so V1. 293 Kelvin is your T1. And then your initial pressure of hydrogen is the pressure over the water, so that would be the 722. So 722.2 over the volume of 2.58 over the temperature. The initial temperature is 293. And then we need to figure out what our second set of conditions are for the P2, V2, T2 side. And so our second pressure, remember this is at STP, so what is our pressure at STP? In millimeters of mercury. It has to be in millimeters of mercury because our initial pressure was in millimeters of mercury. 760, good. It's asking for us to figure out the second volume and what is temperature at STP. 273, very good. And then you can do the algebra and the cross multiplying to get your second volume at 2.28 liters of hydrogen. So did our volume increase or decrease? Decrease. Does that make sense for our pressure increasing? If our pressure increases, what happens to our volume? It decreases. So that does make sense. All right. Diffusion and effusion. This talks about particles actually moving and colliding. So diffusion is the tendency of molecules to move from high concentration to low concentration until they are at an equilibrium. Gases move rather quickly, liquids will move more slowly, and solid particles do not move at all. Effusion is then the process of a combined gas to escape through a tiny hole in its container. Like I said earlier, this has everything to do with the size of the molecules. Gases with a lower molar mass effuse and diffuse faster than things with a higher molar mass. So if you're small, you move fast. If you're big, you move slow. Graham's law is that the rate of effusion or diffusion of a gas is inversely proportional to the square root of the molar mass of the gas. Let's see. I think I have a nice formula for you. Yeah, so you'll take the square root, and then it'll be the velocity of one gas, or not the velocity, I'm sorry, the mass. Oops. Mass of one gas over the mass of the second gas, and this order will be dependent on how the question is phrased. Okay? All right, so to calculate the ratio of diffusion rates for ammonia gas and hydrogen chloride at the same temperature and pressure. So we need to figure out the velocity. Not velocity. Why do I keep saying velocity? It's the molar mass, sorry. We need to figure out the molar mass of each of the compounds. So the molar mass of NH3 is your 3 times 1.007899. We'll just go 8 plus the 14.007. And it looks like that should get us 17.04-ish grams per mole, depending on how you round. And then NaCl is just the 36.46 grams per mole. HCl, yeah, you're right. Sorry. And then it's asking calculate the ratio of diffusion rates for the ammonia gas and hydrogen chloride. So remember, with ratios, order is important. So it lists ammonia as the first one, so that will be your numerator. Sorry, I did that backwards. 17, right? Ammonia is 17. Okay. And then to hydrogen chloride, which is 36.46. But then with Graham's law, it says the inverse. So what do we have to do once we set up the ratio? Flip it. So once you apply Graham's law, it's the square root of the inverse. So 36.46 over 17.04. Then you can run it through your calculator. When you do that, you should get a value of 1.46. So what the heck does that mean, 1.46? So this means that the rate of diffusion of ammonia is 1.46 times faster than the rate of diffusion for hydrochloric acid. And this makes sense because NH3 is a smaller molecule by mass than hydrochloric acid is, looking at their molar mass. So remember, if you're small, you move fast. If you're big, you move slow. Okay?